Our next item on the agenda is our blockchain, the ultimate distributed system paradigm shift. This is going to be from Maurice, and I would like to introduce Maurice to the stage. He has an AB in mathematics from Harvard University and a Ph.D. in computer science from MIT. He has served on the faculty of Carnegie Mellon University, Brown University, and the staff of DEC Cambridge Research Lab. He is a recipient of numerous awards, which is a long list, by the way. And these aren't like, participation trophies. These are real awards, like legitimate awards. So I'd like to introduce Maurice to the stage. Thank you.
Thank you. Next slide, please. So you may have noticed that Bitcoin is very much in the news. Now, my attitude toward Bitcoin news is kind of like when you're driving on 95 and you see there's an accident over on the other side of the road, and you know you're a really bad person because you kind of slow down and gawk at it, but you can't resist. And much of the news, particularly in the early days of Bitcoin, had this kind of flavor where it was kind of appalling, but you couldn't really look away. Part of what's driving the interest is, of course, this idea that something that cost about a quarter 10 years ago is now I think it's 7,000 today. It was almost 20,000 not so long ago. So there's a real roller coaster ride going on, and nothing attracts people's attention more than the possibility of winning this kind of a lottery. Now, Bitcoin came to the attention of most people with the discovery of Silk Road. So Silk Road was the place to go to buy drugs, weapons, murder for hire, bootleg albums, all kinds of things. It was notable because they accepted payment in Bitcoin. And they accepted payment in Bitcoin before Bitcoin became a household word. Then when the FBI shut it down, and it made the news, then that's how most people heard about Bitcoin. So in the popular imagination, it's associated with Breaking Bad style culture. There are lurid stories of people who have lost zillions of dollars. Mt. Gox, as I'm sure all of you know, was a large centralized wallet. Large amounts of Bitcoin vanished, and to this day, nobody really knows why. It's not clear whether they were stolen, whether they were embezzled, or whether they were lost just from carelessness. But this is the kind of thing that makes headlines. Things that where you don't lose your money tend not to make headlines. There's this kind of Saturday night comedy sketch like story where the person who invented Bitcoin was some entity who called itself Satoshi Nakamoto. And to this day, nobody really knows who it is, but we still have people who claim to be Satoshi Nakamoto, kind of like the Princess Anastasia or the Lost Dauphin. And there are all these comedy routines where somebody comes up and says, "I'm Satoshi," and somebody who should know better says, "Yes, I believe they are," and somebody else says, "Well, wait, this can't possibly be for all of these reasons." And this is another kind of excruciating drama that plays out. And again, you can't really look away from it, even though it's kind of horrifying to watch this. But this ends the lurid and sensationalistic part of the talk. So I'm not really going to talk about Bitcoin as such. The reason that I bring this up is in the popular imagination, again, Bitcoin and by extension all of crypto has a slightly off reputation. So what I want to do in this talk is talk about blockchains, and in particular I want to most of my talk will be talking about the technology and kind of demystifying it. There's a lot of mysticism and so on about what blockchains are, what they do. This morning in the New York Times, I don't know whether I was amused or alarmed to see that there was an article that was talking about the fact that a large, highly prominent federal investigation was split into two teams. And they said this is a blockchain prosecution strategy. It's, of course, had nothing to do with blockchains, you know. But you know, this means that the word has entered the you know, mainstream popular culture, and I'm not sure whether that's a good thing or a bad thing. But I'm going to talk about mostly about the technology and why it's not as scary a thing, and why you can understand as much as you need to know without having to work too hard. And then I'll talk a little bit about where we're going with this and kind of how this fits into the Ethos vision. So this was the original Bitcoin paper. Question here is, if this paper back in 2008 when it was written had been submitted to an academic conference, would it have gotten in? Now, of course, we don't know because it wasn't, but my suspicion is that it probably wouldn't have. Now, in most research areas, despite what people tell you, real innovation always comes in from the outside. There's always something disruptive. That my colleagues and I were very good at improving earlier results because we know that our papers will be accepted in these conferences and we can check off the boxes on our CVs and get tenure and grants and so on. But writing a paper that's really radically different is a very risky thing, and by the time people recognize that you were correct, you know, it's too late. So in this case, this paper came from outside our community. It was ignored for a long time. Most of the work in this area was done by gifted amateurs and not so much by researchers. So one of the things I'm also going to talk about is you know, how this needs to change in the future. So you know, now it's a big deal, and it's probably you know, more important than a lot of the things that were published in our conferences back in 2008. So the basic idea, all a blockchain is a distributed ledger. So a ledger is an invention of the Italian Renaissance, a very distant precursor of cryptocurrency. And the idea is that it's an append-only list of events. It's append-only because it says that you're not allowed to erase anything. So in double-entry bookkeeping, if somebody tries to steal something, you're going to detect it because you'll notice that the things don't add up, or that funny things are happening. If you can go back and erase things, then you don't really have much security. So the only thing that's going on here is we're building a tamper-proof ledger with append-only behavior. And you know, once you understand that, you pretty much understand the bedrock foundation of what's going on with all of the cryptocurrency stuff. Now, it's important to realize that it doesn't have to be financial information. It can be things like copyright rules. It can be things like what was the temperature in the shipment of ice cream that we sent across the country, all kinds of things. It can be any kind of information that's useful. So in order to talk about these things, I'm going to tell you a couple of stories. So let's say Alice builds a trading engine where she's trading some kind of assets, doesn't matter what. And she has retail stuff going out one end, wholesale stuff coming in the other end, and she's pulling in things, packaging them up into packages, and then selling them. And she has a concurrency problem because there's a lot of things going on at once. There's a lot of orders coming in, there's a lot of shipments coming in, and they all have to be reconciled. So the first thing that you learn if you take a course like the one that I teach is that you can deal with concurrency by putting a lock on things. Same way we deal with concurrency in bathrooms. We have a lock on the door because we don't really want multiple people using it at the same time. In the same way, you can do that here, but that doesn't work too well because there's a lot of things going on, and if everything has to be serialized, then you don't get enough throughput. So the next thing you can do is you can say, oh, no problem, I'm going to replace one lock with lots of little locks. And this is, as every person who's ever written a high throughput concurrent program knows, a recipe for disaster because it's really hard to get that right. And you get deadlocks, race conditions, all kinds of stuff. So finally she decides, okay, we need to kind of rethink what's happening here. And this is something that's well studied in the concurrent programming, concurrent algorithms world. And the way we can do things is we can say, well, let's represent the whole state of the system as a list of things that ever happened. Now that should ring a bell somewhere, because this list of things that ever happened, this append-only list of things, is actually one way to implement our ledger. So a ledger is a list of entries that's just a linked list. And so what we can do is we can divide things up into the operations that happened in order, which is our ledger. Then over here we have all the things that want to happen. And all we need to do is to figure out how all those things coming in are placed onto the list. And this is something called consensus, which has been studied a lot. I'll talk a little bit about consensus, because understanding some of the issues here will also help you understand things like proof of work and proof of stake, things that you have probably heard about. So in consensus, we have a bunch of threads, a bunch of activities. Each of those little chip things represents a process or a thread or an activity. And just to make things kind of abstract, we'll say, well, they all have some input. They communicate with each other, and then in the end, what they have to do is they have to decide on one of those inputs as being their outputs. So here, everybody picks the green thread's input. Now, you might think this is a kind of a ridiculously simple thing to do. What's all the fuss? But it turns out that this is a kind of a distillation of the whole problem of synchronization. So if you can solve this consensus problem, you can almost literally solve any synchronization problem. There's a lot of engineering to make it more efficient, take advantage of special circumstances, but this is really what's going on at the heart of consensus. So everybody agrees on the same value, so we want agreement. Then the next property we want is termination, so that if you don't drop dead, then you finish in a finite number of steps. And then finally, we want to make sure that the value they decide is actually one that they're supposed to decide. So these are the three properties that, that we want with a consensus. And this is exactly the kind of things that we want on our blockchain. There are some subtleties, and sometimes we kind of only approximate these, but in an ideal blockchain, these are the three properties we want. Everybody agrees on what's on the blockchain. Everybody decides without getting stuck. And so this is this was first studied in things like shared memory systems, operating system kernels, file systems, and so on. But it's really the same thing at a certain level of abstraction as what's going on with blockchains. So one of the things about this is you might say, well, this looks a little bit kind of clunky and inefficient, and it's true that there's, I'm glossing over a lot of engineering. This is sort of the basic idea. But what's nice about this is it works for anything. You can represent anything as just a list of what happened, and then you probably want to keep stuff on the side to make it more efficient, some kind of digest, but we won't go there. But the ledger part is simple and sequential. It's really hard to miss what's going on when you just have a kind of a log or a list of everything that ever happened. And then the consensus part is where we put all of the concurrency and all of the fault tolerance. So in some sense, we've split out the sequential functionality, and we've taken all of the confusing, difficult, dangerous concurrent part, and we've stuffed it into this magic consensus box. So that's where all of this mystical stuff happens. Okay, next slide. So what you do looks kind of like this. You say, well, you get the next operation, you join the consensus. If the consensus chooses you, then you're done. And you can generate a response saying, yep, your transaction happened. And if the consensus doesn't choose you, you go back and you ask again. And this is basically what happens in every blockchain ever, with a few bells and whistles added on. And so this is the universal construction again. So the next thing we can do is we can put in hashes to make it tamper-proof. So when you're building operating system kernels and things like that, you're not really worried that the participants are going to try to cheat you and steal from you. Of course, in the blockchain world, that seems to be all that we ever worry about. So you can make this sort of thing tamper-proof by just having every entry have the hash of its previous entry. And this way, if somebody changes so much as 1 bit, then the hashes don't add up, and you can instantly detect that there's a problem. So let's say, so Alice's trading company is so successful, she decides she's going to branch out into frozen yogurt. Why not? Then it turns out that she has a problem. And the nature of the problem is that frozen yogurt shipments show up and they're melted. When she opens the container and there's nothing but multicolored glop. And this is super bad for a business. So the problem is when she goes and talks to the people on her supply chain, everybody says, Bob, who ships it, says, well, actually, it's not my fault. And Carol, who makes the frozen yogurt, says it's not her fault. So basically, Bob says, well, I didn't deliver that shipment. It was perfectly frozen when I delivered it to you, and it was already melted when Alice gave it to me. So there's no way to contradict that. So it's basically Bob's word against everyone else's word. And Carol has similar kinds of excuses. So Alice decides that she's going to blockchain her supply chain. So what's the advantage of the blockchain here? Well, it's got nothing to do with the usual things that we talk about when we talk about cryptocurrencies. What it is, it's a tamper-proof record of what actually happened, which is exactly what she needs to do to figure out who is responsible for all this melted yogurt. Next slide, please. So what she does is she'll put the ledger in the cloud, and she'll put sensors in trucks and a factory that just measure the temperature. And the sensors here, well, sensors are unreliable, and Bob, the trucker, might try to tamper with them. So what we're going to do is we're going to get a bunch of sensors, and we're going to have them sort of do consensus on the temperature before they go on. So here we have I replaced the numbers with different fruit. So normally when we worried about consensus before, the problem was we were worried about crashes, worried about somebody becoming unresponsive. But in this case, where the sensors can go haywire, and where Bob can tamper with them, we're worried about a different class of failures, which are called Byzantine failures. So here we have an evil corrupted process, evil corrupted sensor, that starts lying to the others about what the temperature is. And this is somewhat harder to deal with than somebody who's just unresponsive, because you can use timeouts and things like that if somebody doesn't answer. But if somebody is actively, maliciously lying to you, then it's harder. So this is called, for historic reasons, Byzantine consensus or Byzantine agreement, and these are called Byzantine failures. There are actual practical algorithms for doing Byzantine consensus. They don't really work for things like cryptocurrencies for reasons that I don't have time to talk about here, but I'm happy to talk about it offline if anyone's interested. So the way Alice can set up her supply chain is we have sensor readings. They go into one of these practical Byzantine fault-tolerant algorithms, and they spew out a record of what the temperature is. And so now, if the frozen yogurt shows up, we also keep track of who has custody at each point. So when Carol gives the yogurt to Bob to load on the truck, they sign something saying, yeah, we transferred custody. And then when Bob delivers it, Alice and Bob sign a certificate saying, yep, we transfer custody again. So if something bad happens, all you need to do is look at the blockchain, and you can take that to a judge and say, see, this is tamper-proof. It's totally obvious that the yogurt melted inside Bob's truck. Bob is liable for the damage. And so that means that everybody's problems in some sense are satisfied. The supplier and the factory are protected against malicious accusations, and Alice knows whom to blame if her yogurt shows up melted. Now, the important difference between this kind of consensus and the kind of consensus that we talked about with the trading is that the participants have identities. So here, each sensor has a serial number. Alice and Bob have signatures. Now, when you start thinking about something like Bitcoin, the participants don't have identities. You can't do voting based on IP address because it's easy to fake IP addresses. You can't do voting based on driver's license numbers because you can make up driver's license numbers. So there's a big difference between the kind of consensus you can do when you have identity and when you don't have identity. And this is something that will be important as we go along. So yes, okay, next slide. So, okay, now Alice sells her frozen yogurt business and she opens a restaurant. So now, what she decides, now she needs to raise money for the restaurant. So we all know that in today's day and age, there are many ways of raising funds. So she decides to go with wait for it. Actually, no, not that, next slide, no, forward. Next slide. Initial coupon offering. Initial coin offerings or so yesterday. So this is a coupon, and it's not just a coupon, it's a crypto coupon. And what's it good for? Well, it's good for discount meals when the restaurant opens. It's a utility crypto coupon. So you buy this coupon, Alice will use it to buy a deep fryer, and when the restaurant is operating, you can get a discount meal. Of course, what Alice is hoping is that people will buy these coupons and a secondary market will arise and they'll increase in value and people will speculate on it and so on. Now, the way that we certify these things is we use public key cryptography. So Alice can encrypt something with a private key, decrypt it with a public key, and what the coupon says is basically what you see there. It says anyone who knows the private key that matches the following public key owns one of Alice's crypto coupons. And so here we're using the public key, private key difference to create these coupons that can't be forged, but they're purely electronic and they can be traded. So this is how Alice creates the coupons that she's using. So the private key is used to convey ownership. The fact that I know the private key means that I own the coupon. The fact that the public key there gives you proof of ownership because I can sign things. So the private key is ownership, the public key gives you proof of ownership, and then the blockchain itself, the ledger, gives it value. Because if this coupon is sitting on the blockchain, then we know it's real. So these three components, ownership, proof of ownership, and value, are given to us by the blockchain, the public, and the private keys. And there's no magic to it. So if Alice wants to trade a coupon, suppose she wants to take a coupon and split it into two pieces, then you put something like this on the blockchain. So you prove that I own the asset by signing it. So it's saying I, the owner of this asset, hereby give it to split it 50-50 between these two public keys. And since that public keys are common knowledge, everyone, that's easy to define, then, when this appears on the blockchain, that means that I've basically taken the coupon and I've destroyed it. I've broken it into two smaller coupons the same way if you take a $20 bill to the bar and they give you two $10 bills, you don't have that $20 bill anymore. So this is how we avoid notions of accounts and balances and so on. This is called unspent transaction output in the jargon. Now, this is where it gets interesting. So Alice doesn't want to maintain the blockchain herself. You know, that's it's expensive. People might not trust her to do this right. So she has an idea. I'm going to outsource this. I'm going to create a community that is going to maintain my coupon blockchain for me. And how do I convince them to do this? Well, I'll reward them by giving them more coupons. And for obvious reasons, we'll call these people miners, even though that doesn't quite work with the restaurant analogy. But so the miners are the ones who figure out which coupons are valid. So this is the sort of mystical meaning of being a miner, is you get to decide which transactions are valid and which ones aren't. Not you individually, but you collectively. So you can individually decide all kinds of nonsense are effective coupons, but if the other miners don't believe you, they're not going to build on your coupon, and you'll never collect your reward. So there's a kind of incentive for everyone to behave themselves. Now, in order to mine, however, the classical distributed computing work on voting, and there's decades of this, all assumes that, well, it requires voting of the kind that's familiar to us, but that kind of voting requires identities. So what happens here? So this is the Delphic Sibyl from Michelangelo's Sistine Chapel. You know, there's several levels of puns going on here. So our friend Sibyl here likes to vote. And in fact, you know, she likes to vote a lot. And having a large collection of voters that are secretly controlled by a single entity is often called, and no, it's not Cook County, it's a Sibyl attack. So, returning to what I said before, if you allow people to vote based on things like IP address and so on, it's super easy for a bad person to create all kinds of fake accounts, like Russian Twitter bots, and vote. So we need some way to prevent that from happening. So this is something that sociologists are well aware of. And you know, think about who else has this problem. So imagine that you're organizing some kind of a street gang. And you need to decide if someone wants to join your gang, how do I know that they're not a plainclothes policeman or a newspaper reporter or just a freeloader? Well, you get them to do something that is expensive for them, that they wouldn't do if they weren't sincere, like get a tattoo. So if somebody says, you can join our gang if you get a gang tattoo, then you're going to think twice about it, whether you're serious. So costly signaling also shows up for things like mating. So you know, male peacocks and Irish elks have these huge displays that are, you would think would evolutionarily not a good idea because he would attract predators. But they're a way of showing to the opposite sex, you know, I am so awesome that I can get away with this display and still, you know, be a bad peacock. You know, you can also use it to demonstrate that you belong to cultures and things like that. So the use of expensive signaling to do consensus is called proof of work. And it isn't literally burning money, but that's the right way to think about it. So you want to know whether I'm serious about Ethos? I'm going to set a $100 bill on fire and wave it. And at that point, you know, you might have other opinions about me, but you know that that I mean this. You know? And the same way, this is how proof of work on blockchains works. So proof of work was actually invented as a way of controlling email spam long before Satoshi came along. It never really caught on, although it seems like a good idea. And probably, I think the one real insight and innovation that went into the original Bitcoin idea was this idea that you could use the Dworkin-Nauer proof of work to do consensus. And again, it's expensive and it's hard to fake. So here's how to think about it. What we're going to do is we're going to hold a lottery to decide who gets to append the next item onto the ledger. So what I'm going to do is say, okay, so you all want to be miners. You want to decide who goes next. I'm going to sell you a very expensive lottery ticket. And you give me the money up front for the lottery ticket, and if you win the lottery, then you get a reward that's bigger than the cost of the ticket. The rest of you, tough. You get nothing. And so then if you want to be a miner, you keep buying these expensive lottery tickets, and every now and then you win, and the hope is that you win often enough to pay for the tickets. In this case, tickets are electricity bills. Or, what you pay for the ticket is your electricity bill. But it also, you only get paid if all the other miners agree with what you're doing. So that means that that's an incentive to behave, because if you go wild and start visibly cheating and so on, the other miners are going to ignore you and you won't get paid. So it's like you buy a lottery ticket, but before you can collect, all the other lottery winners get to vote on whether you get your money or not. And also, that means the civil attacks don't make any sense. I can have an army of sock puppet bots, but if they have to pay money for the lottery tickets, it doesn't matter. So, starting to wrap up, most of the work on cryptocurrencies, as I said, came from outside the research community. Like any truly disruptive anything, somebody non-established has to think of it. Nevertheless, I think a lot of what they've done, there's a lot of very creative work that happens there, but my frank opinion, and this makes some people angry, is that a lot of what they've done is reinventing a lot of notions from distributed computing in this kind of, bizarro alternate universe way. So it's not exactly the same, but there's a kind of one-to-one correspondence between many of the ideas. And when they invented these things, they didn't always do it right. And so what we need to do is the time has come to take the kind of more established science and apply it to cryptocurrencies and blockchains. So there's a classic Star Trek episode where Kirk and Spock go into a time warp and they meet their evil doppelgangers. You can tell I've labeled it for your convenience, but you already knew that the Spock with the beard, that's a universal signifier of evil in 1970s America. And we won't even talk about the muscle shirt that Kirk is wearing, which is also clearly something to be aware of. And so the analogy is clear. The cryptocurrency. The blockchain people are kind of the bad boys of the distributed computing world. And what we need to do, I think, is to bring these two communities kind of closer together. Not out of sort of, kumbaya-like friendliness, but because I think we all need to do this in order to make progress. The cowboy era of blockchain, I think, is time to wrap that up and move on to something else. These are all of the things that are subject of classical distributed computing, which show up in blockchains, often under a different name, and often, a little bit changed, but not that changed. So, blockchains are not all that different from stuff that we've been doing for a long time. They're different enough to be interesting, but we really need to kind of get serious about pulling in all this older technology and putting it to work on this stuff. So what the next step is where is kind of the reason that brought everyone here, which is that I think the technology behind blockchains, I hope what I've done is I've kind of demystified it. Some of you know this perfectly well, but the rest of you, I want to say, well, this is nothing mystical, nothing magical. It's really just all these old kind of familiar pieces glued together in a slightly new way. But the technology might be kind of vanilla, but the purpose of the technology is really the revolutionary part. the things that we can do with this technology that we could have done all along, but it never occurred to us to try this before. That's what we care about. So how is it going to be revolutionary? Well, disintermediating trust. Now, I know that sounds like a business school buzzword, and you know, if somebody said that to me, suddenly I would just recoil. But what it means is that we can take these institutions, stock exchanges, you know, Spotify, Facebook, things like that, and we don't need to trust them to do things for us. We can use blockchains as a way of saying, well, we can collectively trust one another through this mechanism. So you could set up an alternative to Spotify, for example, where both the customers pay less and the artists get more, because we can use you know, blockchains and smart contracts and things like that to enforce copyright and fair payment and so on. So we can, you know, I mean, ICOs are already an example of bypassing venture firms to a certain extent. You know, that there's kind of a rocky road there, but it's still, you know, something to worry about. And the other thing we can do is we can make, this opens up a whole range of new financial instruments. Now, these financial instruments are not going to be very useful if they're only accessible to kind of ultra geeks or people who are so rich they don't care if they lose their money. This will be revolutionary only if we can make these things kind of safe and usable for everyone. You may have heard this before. So the next stage of the sort of blockchain universe is law and order. And when I stand up and say this, this sometimes makes people seriously irritated because, of course, blockchains came out of this kind of libertarian, we don't need no government courts, police background. But the problem with code is law is that code isn't law. Law is law. And if you know, the government, regulators, all these things are going to come down hard on anyone who isn't aware of this. And the reason that hasn't happened so far was up until now, the blockchain world wasn't important enough to be noticed. It was totally under the radar. Now that it's no longer under the radar, you know, we have to figure out how to move forward in a way that's kind of compliant. So we want a world that's actually run by grown-ups. I know that's not a very, doesn't sound very revolutionary, but in this case it is, because so far that's not been what's happening. We need to do best practices. You know, we should, you know, one of the exciting things about this field is you wake up, pick up the New York Times, and first page of the business section, oh, $100 million were taken from this wallet or that particular DAO and so on. And you know, this kind of amateurism has to stop. Things like regulatory compliance, again, the you know, this is alien to the ideological background of a lot of the founders, but sorry, this is, you know, time has come to make peace with this sort of thing and, you know, move forward in a way that works well with all this stuff. Okay, so is that my last slide? Yes. Okay, that's it.